to record this so everyone has on the video on recording. Hello everyone, welcome back. So there's no class on Friday. I totally messed up. I have capstone presentation going on at the same time, so I can't be here. So I don't know if you're excited or you're sad, but I hope you're sad. So I had to take one of the classes that I created and one of the assignments off. So you'll see them next week, but you still have to do the velocity kinematic. That's due on Friday, no matter what, right? Just a good day. Okay, with that, we're going back to our lecture today. And me being me, I didn't charge my pen, so I'm going to be talking a little bit until the pen is charged. Well, the little bit at the beginning is just talking. So you will see this is slide first. So this is basically our motivation. And today we are moving into inverse kinematic. So as we talked last time, you know enough to solve forward kinematic problems. So forward kinematic problem was that if I know how much each joint moves, where does the end effector end, right? Now, the actual problem in real world is that your robot needs to go and pick up this cup of coffee and it's sitting over there. And let's say we know where it is. How should the robot approach and grab that? Meaning that how much each joint has to move in what direction for end effector to end up there. And you see that the end effector is the gripper, right? Sometimes we use gripper. The only thing it does is grips and like secures and then come back. That's why we don't care about right now what the gripper does. We just want to know where the wrist will end, because from there is just an action that happens. And there are a couple of other things that will be involved, like force control. So make sure the cup doesn't slide through. So it's a different kind of control is involved in that. So in our inverse kinematic, we also care where the joint will and needs to go. Now, from everything you learned so far, what do you think? Let me go to the previous slides. I want to give you an opportunity to think about this. So how would you solve this task? This is the robot arm, right? It's 2R, right? Well, 3R here, 1R here, 4R. If you want to be correct. So this is the home position of the robot R. What should happen for this to end up here? What do we need to know? And what do you think you should approach this problem? This is where you think and then raise your hand or not and talk about it. And you can say, I saw in this movie they did this, or I think they should do this. It's fine. I just want you to think about it. Oh, you were not raising your hand. Okay.
Well, I feel like there's a lot of times maybe one set of sort of same position, right?
Mm-hmm.
So it's hard to find the first one for that reason.
Very good. So first thing, so one of the, let's say, issues, I'm just going to call it issue or challenge, is that there is no unique solution for this, because I can go from here, or I could do this, or if I could do this. So all of this grabs, so the task will be done. Now, how it is done? So there is no unique solution. So that's one of the challenges, meaning that there could be different ways. Now, how do we choose a solution? What would you think is important to pick one solution over another? Most efficient. Now, when you say efficiency, what do you mean? One is energy spent, right? Which brings to cost and money. What else? How does time is spent in so when we say cost, you might think what's the cost of this arm going from here grabbing or from here grabbing here? So it doesn't directly shows cost, but there are things that it means cost. What are those things? What in robotic application could be reflected as cost? Yes.
The electricity cost.
So let's say that you're running the motor, it goes 45 degrees or 35 degrees. It's not going to be a big power consumption issue. What? Yes.
remember what the was.
So if you could, so time is cost, right? So if you, let's say your solution, because the way that you solved it is a slow, that accumulation of like repeating a task 5 times would be 10 minutes. If your solution was faster, it was 2 minutes, it could build 7 things instead of 5 things. Let's say it's a welder, right? It could weld 7 lines instead of 5 lines. Then now there's a cost, but it came from the time that takes for your solution. The other thing is the processing power. That's also cost, right? That's also time. The time comes from that. How fast we can solve this. So fast means, well, your actuator have to be fast, but again, your controller has to be fast, right? So with inverse kinematic, there are more topics and issues involved than just simply, okay, how much this thing needs to rotate. All right. What we do here in our inverse kinematic, though, we are just going to pick one problem. We say, okay, first of all, let's solve and figure out what are the possible solutions that can happen, right? Then a next level would be now pick which one. So in our inverse kinematic, we're going to solve the first problem. What are the possible solutions? Sometimes there are many possible solutions. Sometimes it's a lot more limited. Okay. The other thing that you need to pay attention for inverse kinematic is this space that the robot can work in it, like the workspace of the robot. So you can't go outside of that. Now, a lot of time also you have obstacles in the workspace. Your robot has to go around it to do the task. What we do here, we make it simple. No obstacle. Just the workspace of the robot, because the robot can go 0 to 90, for example. It can rotate 0 to 90 or can go 3 centimeters. That will be all the limitation we give. So we are making our problem very simple. So you see that the example we solve, we basically go right into examples because this is the best to learn from examples. And you'll see that it seems so like I think it's very intuitional. Like you use like, oh yeah, I would do that too. But then that's just the first step because we simplified our problem so much. So don't expect to be able to solve a problem just by knowing, Dr. Z said this is inverse kinematic. We're simplifying a lot. We're trying to solve one problem at a time. All right. We will hopefully get to like a little bit of path planning and maybe obstacle avoidance at some point, depending on how we move forward. All right. So this is, I think, your first slide, right? So here's an example of like what you mentioned, a 2-lane planar chain. Let's say that you need to get to point X and Y, right? And for the robot, if we just concentrate on position, so right now we're not talking about orientation and this is fine. If you need to reach X and Y, we can use geometry, right? We said whenever we have 2D robot, the best way is just do geometry, like trigonometry, and then it's like sine, cosine, theta, and so our equation, our F, would be those two, and then we can solve this mathematically. And there will be 2 solutions, righty and lefty, or the lower arm and the upper arm. To solve this problem, the robot can go either way, and both of them are correct. So this problem has 2 solutions. It's 2D, to reach one point, you can go 2 ways, and both of them are correct. Now, to pick which one, then you have to look at the other condition of the question, right? So this is one way. We will get back to analytical method, but it will be this. There will be literally a geometry problem to solve. And there is sine, cosine, there are usually angles or distances that you need to find out. You will try to find as many equations as you have unknown and then solve it. That's one method. The other method would be, going back to my second slide. The other method would be your geometrical method that I'm starting from here because I think this makes sense and this will kind of lead into the analytical method as well. The third method is your numerical method, which actually is widely used in industry. So sometimes to solve those analytical problem, you have to do it numerically. All right. So your book is like has like extensive, I think examples and methods on the numerical part. I believe for numerical method, you actually have to do a lot of like simulation coding. You should be very good with coding part to understand those. So I'm doing that first. So I want to make sure that you understood what the problem is, like how you're solving it through those more accessible methods. Then we will take a look at the third part. All right. So if you're following the book, I think this will show up and then this. I'm going to be able to discuss. I found it very useful. It's not from your book, but the premise is very simple. Again, the task of inverse kinematics is given a forward kinematic in position and orientation of your end effector, or where it should end up. What are, can we find a solution that satisfies, solution for joint variable that satisfies that forward kinematic? Okay. Did all of those make sense? Understood? Okay. So, yeah, let me go on then. You come back to this again. So here, let's say we have a cylindrical robot. So this is a RPG robot. You see that you have all the axes given to you. You know how to assign axes. If you have been assigned, you don't have to worry about it. If not, you know how to do it. Or your practices. In this method, we are going to say, okay, we just saw solving 2D is very easy, right? We have a 3D problem. What can I do? How did the 2Ds? And then I solution all those 2Ds will be a solution because you can look at it from front view, top view, side view, right? So X, Y, Z axis, and then Z, Y axis, and X, Y. So we look at it in 2D plane, and we derive those equations, and we have to solve those, right? That way, it's more intuitional, and then it's easier because you don't have. I just saw you try to figure out which way it moves, but when you go to those plane, you can literally see like which way and which joints move in which plane, which is very powerful. All right, get ready to do some math. Hopefully my pen is kind of trash because I can't talk more. If you didn't know this, I was just trying to talk to chargers. All right, so the question is find inverse kinematic IK expression for given RPP manipulator. All right. This means that we're trying to find the position of our third frame here in frame 0. So again, we are trying to find the end effector still with respect to base frame because we are using a forward kinematic solution, right? So the position that you're asking is with respect to base frame. So we're going to find that with respect to base frame. First, identify all your joint variable. So let's take a look. We have theta 1, D2, D3. So theta 1, D2, D3. I expected because I know this is the RPP. And then the goal is to find expression that can solve for the joint variable, right? So if I'm going to call this actually Q. Q is equal to that. So my goal is to find what, to solve for Q. I'm going to start from X0, Y0 plane. Why am I starting with that? I don't know. I saw E3 is just one direction in this plane. It's simple. I'm going to pick that. You could pick any point. So I'm looking top view in these two planes. So start from x0, z0. Actually, z0 is this one. Never mind. So what are the joints that I see in x0 and y0 now? x0, z0, sorry. I need to be more careful about this. In x0, z0, what joints do I observe? The motion of which joints are in this plane? D2 moves this way, right? Also D3, because the rotation, I can't see it in that plane, right? So I will be able to see D2 and D3. So this tells me I can find relationship that has D2 and D3 in it if I'm in this plane. So next thing we do, we are going to draw the robot in that 2D dimension. So if I looked here, right, looking at this, I'm going to draw what I see in x0, y0 plane. I see a base. I see this cylinder, but it looks like a box, right? It's a little bit of your mechanical engineers here. Now, what axis do, let's draw all of that, then we draw the axis. No. What do I see next? So I draw that one, I see this guy, A1. Then I see this box, which is my joint. Then I'm seeing this link, A2. Then I see this joint. Then I see this. So when I put a line next to it, I'm just telling myself this is a joint. And this was part of another. So this moves in this direction, in this plane. This one doesn't move in this plane. Then I also see this link that is A3, right? And then I'm done. I don't see anything else. Now I'm going to show all the frame axes that I see. So I'm going to assign the frames to every one of those based on the original picture. So here I have x0, z0. Here I have z1, x1. Here this is, I see y2, z2. And at the end of this, I see y3, z3. Do you agree with all of this? Now, you could ask, okay, so why these axes are not all x0, y0? I was not changing the axis. I'm just looking at this from this view. I'm transferring everything here to make it to represent it in two dimension. Now, when we are solving for inverse kinematic, what information do we have about this contraption, about this or configuration? What is this? So can I say this is Z0 and 3? Right? Can I say I also know this is X0 and 3? Right? So this is the position of the end effector in our base frame in X direction. This is the position in Z direction. Now, these are known, right? Because we're solving inverse kinematic, we know the position of the end effector. That's the only thing we know. So in this plane, I know two things, and I have two joints that I don't know what they are. So I have two joint variables. One being this guy, I want to use that color. This is your D2, and this guy is what, D3? So this joint moves in this direction. That's all it means. This joint moves in this direction. So these two are not one. I know what the lengths are, the length. I can fix values, so I don't know that. I also know this distance and this distance. Can we write two equations that these two variable appear in them? This time. Can I say Z0 and 3 that I know what it is, right? I have this value. Is basically A1 plus A2 plus whatever D2 is. It's variable, right? I'm just going to put a star so you know this is a variable. So in here, I know what this is, I know what this is, I know what this is, I don't know what this is. Actually, I don't know. Do on the other side. So I already know the relationship between my joint variable and the rest of the robot. So D2, I put a star, but I don't have to because we know that is our joint variable. Is Z03 minus A1 minus A2. Correct? Yes. What is what, sorry? D2 star? Yeah. So find where D2 is. So I put it a star. You remember why we would put a star next to something? To show as a joint variable, right? So I can take it out. Can you find D2 on the diagram? That's the joint variable. I just put a star so when I'm talking about it, you understand. You don't have to put a star. So what I did is I said, okay, I know this distance from, I know where the Z is, right, from the solution. I know what A1 link is because that's part of the robot. I know where A2 is. So this ended up in this height because of these two plus however much this moves, right? Okay, so that's one relationship. Now, can I do the same thing for X03 to try to find what, because this is in this direction, right? Can I use this or I need to make sure that I look at other things? So this comes to this little line. If this was a P, right, would be fine. But because this is rotation, this link actually rotates and impacts the X direction. So from this view, we cannot write X03. That's why we have to move on to another view. But we already found one of our joint variables, so we need to find two more equations, right, to find the other two. And in the geometrical method, that's the only thing that you need, like it's, I won't say it's a challenge, but I say it's a challenge. Like what plane do we look at to find? But worst case scenario, how many planes do you have? Like three combination, right? Look at all three of them. So you might say, oh, this was useless because this doesn't work. Okay, let's go to that one. You run out of like combination of planes. So let's go to now the one that I wanted to go from the beginning because to me it was obvious that would be the one. X0, Y0 plane from top. Why am I going from top? Because I just see the rotation from top now, right? So I'm going to choose that plane. So I'm going to keep it there. So I'm looking at X0, Y0 plane. Now, again, I'm going to bring a little bit of your mechanical engineering visual abilities here. So if we look at this from top, what do we see? Everything on top of each other, right? So basically it's like a box. Now, to help us to understand like how things are related, I'm going to assume that this one is rotated a little bit. Just show that angle, right? It's like showing in zero position. I'm gonna just give it a theta position. I can see where theta is, right? If I do that, but I'm gonna make sure that I identify where was the home position. So this is the home position. So from top, this would have been my x0, right? So you can't even say this was your x0 initial, y0 initial. We want to be very careful here. If I rotate, all of them are rotating because those two other joints are connected to the rotary. So everything moves. I'm going to see something like this. This box represents my prismatic joints. Let's say the two joints top of each other represented by one box. I also see the cylinder right here, that joint. Now this is the link. If I look from top, the A3 is the only one that I actually see. I don't see A1 and A2. They're projected from top. Now I'm going to identify my axes. So I'm going to redraw this one. It's in the center because right now it's not in the center. Centered. So this would have been where I started. So this was my x0, and this was my initial y0 before we moved. But we moved. Now, in this motion, x1 would be in this direction. Your y1 would be in this direction. So I'm looking at the top here, right? And then I'm going to draw for the second one. That is going to be z2 and x2. Right? The third one is x1. Let me draw something different. This is z3 and x3. Again, all I did, I just projected it in 2D. Now, so the whole goal was to show you this is theta 1, right? Now, again, I know this one is what? Z03. No, sorry, Y. We are in Y. We are in Y coordinate here. So this is Y03, and this way we are in X03. So the orange, I know what they are. Already know. What else do I see from top view? D3. I still see the second prismatic joint moving, right? So I can put that in there too. So now D3 is joint variable. A3 is a fixed link size. All right. If you need to put a star to show that this the difference, go ahead and do that. Now I have everything converted. Now I need to find relationships that my joint variable will appear. So can you think of any? First one should come to you very quickly. And it's Pythagorean. Someone see it? Or you just don't like talking? This is the second one, right? What's that? So we're going to find two expressions, but we're gonna first find the one that's easy and you can see it, right? Can you tell me what it is? So what we did up there, I'm trying to find expressions that my joint variable should well be there. I have two joint variables that I don't know what they are, theta 1 and d3, right? I need to find two relationships that will have this, yes. That's the one that comes to your mind very quickly. Because you know what this is. You know what this is. You don't know what this is. So this is why this is geometrical method, because all you have to do is find those relationships. So first one, very quickly, we say that, wait, x0 3 square plus y0 3 square is a3 plus d3 squared, then a3 plus d3 is square root of x03 squared plus y03 squared. What we were looking for, this guy. So d3 is minus a3. So that's the second relationship. First one was this guy. So I know this, I know this, I know this, don't know that, no problem. I know, I don't know you. So far, we found two. We need one more. Okay. How do you find the other one? Yes. Did someone raise their hand? Yes. Tangent of theta 1, right? So tangent of theta 1 is y03 over x03. Great, we have both of them. So theta 1 is tangent inverse of y03 over x03. Cool. That's the third one. Three equation, three variable. It is not even a problem now because you just have to plug in. So for now, if your robot is supposed to grab something at 1, 3, and 6, x being 1, y being 3, and z being 6, all you have to do is put those on the left side and from the right side. I mean, put those in the right side and then left side is what should be theta 1, what should be 23, and send a command to the robot. If you're simulating, you solve this and you say, now rotate this much, you see when you end up in your code. Simple enough? So the concept is simple. What would be the challenge? Just seeing this relationship, trying to find it. So most of the time, you only need these things. Like, I hope yours is very different from this, because these are my old slides. This is supposed to be a calculus check one right now. Okay, so this is a very simple robot. I brought this for you to practice. So I want you to find the inverse kinematic. Before doing that, the only other thing you need is, like in these kind of problems, is the direction, no, not direction cosine, the log cosine. You know how log cosine works? So I'll bring in the next lecture, we're gonna solve a problem, but the only other thing you need to know is how log cosine. Because you will have three angles sometimes, and then you need to use log cosine to write a relationship. That's it, that's all you need. So when you were told you that when you learn trigonometry, it was useless, tell them no, it's very useful. And inverse kinematic is one of the hardest problems in the world. Given it's not going to be simple, but you know. Now I want everybody to solve this. The question is find inverse kinematic expressions for the PPP manipulator given for the given manipulator, but given here, all right? Knowing P04 is X, Y, Z, 04. So you know the end effector because that is the inverse kinematic problem. Okay. All right. So hopefully this was simple because it's 3p. Doesn't have any sine cosine in it, right? But the goal was to practice to see if you can find those relationships. I'm going to start from x0, y0 plane, which is my top view. And then you can draw that, but you say, Dr. Z, do we have to draw it? No, because this, if it's simple enough for you to be able to write a relationship, you don't have to, but it will help you to draw from top view, do it all the time. So for this one, for grading purposes, I'm not looking for if you're able to draw it from sides. My goal is to see if you can write those relationships, right? So drawing is helping to see them. So starting from here, I see this one, I see that one, and I see this one. So this is A2, A3. And I know this, I can see D2 and I can see D1 here. And I'm going to just practice my axes and frames, X0, Y0, please correct me if I'm wrong, because I'm just following my notes. Z1, X1. And here is Z2, Y2. Here is, this one is important, Y3, X3. All right, that's all I can see. Then I can write these relationship for it. I know this is Y04. This is X04 because why? Because my end effector is right underneath. So it will be the same. So the relationship would be X04 is A3 plus D2. Y04 is A2 plus D1. Doctors, can we stop here? No, you can't. Because that's, you cannot code like that and ask computer to do it for you. So you have to actually do that. D2 is what you're trying to find. D1 is Y04 negative A2. Well, I found 2 already. How many more do I need? One more, right? So here is like, you don't have to write for all the plane. You need to see where can you see D3 from? Then just write that plane. So hopefully everybody got this 2 correct. So I'm gonna write X0, Z0. The things that I can see are these 2 frames, or these 2 joints, and this little guy, because that's the link that the end effector is connected to. This is A4, this is A3, this is A1. Right now I'm just showing the joint variables. You can see the axes in my annotated version. This is D3. And then I'm going to write the other two relationship. So Z04 is A1 plus D3. Make sure this is correct. So Z04 is A1, negative A4, negative D3. So D3 is Z04 plus A4 minus A1, correct? That's the third relationship. So we have all of that. Now, if I tell you, given end effector position, P04 is, I don't know, 1 centimeter, 2.5 centimeter, and 0.1, well, it would be ridiculous, but, and 5, and then having A1 is 0.2, A2 is 0.1, A3 is, what direction is that? X. 0.3, and A4 is 3. 2. Find joint variables.
If you add A4.
Yes, what you will find should be a negative number. Because the direction of positive is this way, right? So you're looking in here. So this is your 0. Look at that. Are you talking about this guy here?
I'm talking about, so you have Z04 equals A1 minus A1 minus D3. You solve for D3 on all the time. This is negative.
Oh, that's what, okay, so my math has problem. So D3 goes that way, and then this becomes negative. This is positive, isn't it? That's what you mean?
Yeah.
Okay. But what I realized, I understood was different. I will tell you what I understood. So D3 goes to the other side. Then we have A1, negative A4, negative Z04, right? That's correct? So what I understood was that why didn't we flip this? Because yeah, we don't care. This would be a positive value. You don't look at all right, so now if I tell you like, so I gave randomly some numbers, I tried to be less than 0.5, so like nothing weird will happen. So if you say that this is the configuration of the robot, right? These are the links, and this is where the end effector needs to go. What are the joint variables? You put all of these in those three equations and tell me the joint variable. What does that mean? Like when you have joint variable, then what do we do with that? So that's the control part. So now you have a value to tell your actuator where to go. And then there are control methods that make sure that you go 3 centimeters that you're supposed to go. And that is, so the thing is, control is part of robotics, but you can also learn it separately. But that's one of the application of control robotics, right? So your job will be, you're telling the controller where to go. The rest of it is different stuff. Make sense? So these are very simple, these simplify the problems, but usually it will give you good ideas. No class on Friday, we'll meet on Monday. I didn't give you an example for this, but Monday I'll bring an example and you'll do that. All right, so we'll be like, check how many times.